you can hear me, could you please give me a green check? So, come on. Go ahead, guys. Could you please give me a green check? Thank you, Byron. There, Joe, my friend. Matthew, I got one from you. Thank you, Joe. Okay, great. Okay, we're going to be doing this tonight. We're going to go over chapter 17. Chapter 17 talk about basic electricity. This stuff will be probably review for some of you. So we're going to go ahead the principles of operation for the science of electricity tonight. But do so, Joe, my friend. Last week we did some. We talked about electrical design and how to lay out equipment and drawings and how to read blueprints and look symbols and line diagrams and so forth. You guys have taken a block exam that I usually do not review. I don't because it's an exam. But I looked at the results and there's certain one really want to go because it was low, score low, and I flashed them for you guys. But I can read and just because they were scored, the majority of you have scored it low, and I believe I should emphasize it. So go ahead and review. Take 15 minutes to review as the block exam. A few pins here in the block exam, and I'm going to move fast on these ones. Any question? Anybody has any question in particular? Any question in particular? Questions in particular you want to discuss, Dan, friend? No, Russ is joining us too. Great. So I'm not going to flash things, guys. You're going to hold your horses here. Watching us talks about the drawing scale are shown on answer, and then when you draw the scale for in either of the above locations, which either you can show the draw scale on the block, title block, or you can show it right next to the drawing itself. So that was a few of you guys scored that one. So like right on title block or right next to the layout or the blueprint. So a second question that you guys scored, a lot of you scored very low on that one. And go. And this one is conductors number 1 or larger of the same size, length, conductor material, and insulation type are permitted to be connected in parallel where all of the above, which is contained within the same cable. Conductors of each phase and neutral is installed in each raceway. So either in each cable, each raceway, or conductors are part of an underground isolated phase system. Underground isolated phase system. Underground isolated phase system is you bring all these are PVC, guys. You can bring phase A, phase B, phase C conductors. Since underground, since there's no inductive heat, so you can put conductors of phase A, 2 conductors of phase B, 2 conductors of phase C. So that will be phase A, phase B, and phase C. This is commonly used, Joe, when you parallel. It's easy to install them if you do it this way. It's only for PVC underground, well, PVC. And when you put the conduit, you have to make an opening in the sphere where all conductors will be in the same opening. So basically 12, the parallel. Another thing that says direct burial cables or conductors must generally be buried twice of. If you don't know what the condition is and you have a cable that direct buried, you bury it at 24 feet. That's kind of the worst of the worst. That says all temporary 120 out the amps need to be part of a ground fault circuit interrupter protection for personnel. Temporary wiring, like temporary wiring, guys, like construction and so forth. Any 120, 15, 20, and 30 amps have to be GFCI. So they have 15, 20, and they add 30 amps. Non-locking time have to be GFCI. THWN-2 conductor have a wet location temperature rating THWN-2, guys, it's rated for 90 degrees, regardless of the location, wet or dry. So that's probably why I confused some of you. That's for an exam. THWN-2, it's for wet, dry location, 90 degrees. When you cable whose only type identification is not suitable for direct varied, the option where UF, yes, USE, yes, XHHW, yes, cable that unless speaking you can't vary it as an AMI cable, unless listed, but generally speaking you cannot vary it. And to stop me or chat if you have any question about that one. It's approximate current in the neutral conductor over 3. This is, I think I went over this, I can remember, and this would be probably confusing for some of you. If you guys have a 3-phase system like this, and I told you that on your German guaranteed. Now here's my 3-phase system, and here's my neutral, and I pulled my neutral. And what they're saying is, if you have a 3-wire system, here's a 3-wire system. You tie to A and a neutral, and a 3-wire system coming out of phase. This is what I'm saying. Here's phase A, here's phase B, and one to phase C. Phase C not tapping into it. So if you have a situation, my friend, and you have a 20 amp here and a 20 amp here, neutral, it will be carrying 20 amp. You will be carrying 20 amp because it's a 3-wire coming out of 4-wire 3-phase system. I tell you, this is going to be Matthew, my friend, and your journeyman exam. So that's this question. I'm sure it confused you. The 3-wire single, it will carry is how much current the neutral will carry if the loads are 20 amp, 20 amp. It's going to be the neutral will carry 20 amp. But different. This is different than the single-phase system, guys, that we are all used to. Probably that's what you get confused. And you put a load here and neutral it, and a load here and neutral it. Give it, and if that was a 20 amp, that's single-phase system, and that was a 20 amp, the total here would be 0 amp, right? It would be amps. That's a single-phase system. Okay, so that's probably. I hope that so see first 3-phase. Single phase, 3-phase, single phase. So I use that one because it's going to be a new test guaranteed. A conductor of that supplies a nonlinear load is not required to be counted as a current carrying conductor. Conductor, guys, the neutral of a single phase system. This system, neutral right in here, that doesn't count as a current carrying conductor because it's single phase system of a single phase system, not this neutral, this neutral. This neutral here does not count as a current carrying conductor, though this neutral will, because it's coming from a 3-phase system. That's also in the German exam. This neutral for the single phase doesn't count. This neutral because it's 3-phase well, 3-phase well. So that's I don't know if that maybe that's was the confusion. Nonlinear. A 5 NM cable is not permitted to be run at angle with joists in unfinished basement where due to the answer secured to the bottom edge of the joist if it is smaller than number 8, 8.3. So 3 and 6.2, 8.3 and 6.2, guys, you can mount them to the joist. Smaller than 8.3 and 10.2, you can drill right through the joist, And an uninsulated conductor in type SE cable is permitted to be used as if you have an SE cable, my friend, and a bare conductor with it. The only place you can use that bare conductor is for equivalent grounding conductor. There's a lot of you scored low on one. Electron non-metallic tubing is permitted to be ENT, guys. ENT is permitted to be encased in concrete for direct earth burial. For the most part, encasing concrete is the most accurate if you go to the description of the encasing concrete. Surface meter raceways are permitted to be installed. Our answer for that one was under raised floors. Under raised floors. Moving on to clamps are not required for non-metallic sheet cable entering. Are not required for non-metallic sheet cable entering a single gang non-metallic box. Single gang non-metallic box. You know, they're not required. The clamps are not required for it. And same token, guys, if you have non-metallic sheet cable, must be secured within inches of a non-metallic box without clamps. This one, my friend, also on your German exam. If you box a non-metallic box, guys, use my non-metallic box. There is no clamps. So like my cable, NM cable, you have to support the NM cable, guys, every 8 inches. If you clamp on it, no clamps. Here's my NM cable, and I have a clamp here. I have a clamp. Then you can support every. It's just from here to here. You can support every. Oh, maybe this is not a good. So here's the clamp. Here's my clamp over here. I can go all the way to 12 inches. So that's the people, guys. If you have a clamp, 12 inches. If you don't have a clamp, 8 inches. And I guarantee you on your exam here. Okay. Not required. Okay. Boxes of not of with cubic inches that contain devices and have the threaded entries. This is 100 cubic inches, guys. Boxes of not over 100 cubic inches that contain devices and threaded entries or conduit hubs identified for the purpose are permitted to be supported by 2 or more conduits threaded tight and secured within 18 inches. That's directly from the rigid conduit and the boxes. Aluminum cover conductors. If you have an aluminum conductor and a cover conductor, can you put them under the same terminal? Yes, if the terminal is rated for them. So you grab your conductors, you put it in this side, the other one goes inside, and that terminal or that block is rated for them. The answer is yes, if the terminal or the plot of the lug is rated for them. Any question, guys? Anybody has any question about that? Any questions, friends? This surprised me, guys. This surprised me where it says of equipment rated or less, the amps of the connected conductor must be rated at 60 degrees unless marked otherwise. So equipment rated 100 amp or less, and basically the connected conductors. So if you have 100 amp or less, so I'm going to do that. 100 amp or less. Here's my current. 100 amp or less. Then you go to the 60 degree column. You guys remember that? Amp or less, 60 degree column. 100 amp or less, 60 degree column. More amp, you have the 90 to the 75 degree column. So basically, if the amp are more than 100 amp on the conductor, then you go to 75 degree column. As we size conductors for equipment. So basically, what I thought, guys, just fly through a few of these. Any question, my friends? Any question about the block exam? And their friend Joe, Joanne, for chat. This one here. I need the Joe, and then I need your attention, my friends. So make sure you guys stick with your friend chat here because we're watching. Yeah. That's basically what went over, guys. Action so far before I go and start with basic electricity. Any questions before we basic electricity? So tonight, my friends, from now on, guys, we're going to spend, tonight, we'll spend 1, 2, 3, 4. We're going to spend, my friends, 4 lectures on basic electricity, and 5 lectures. We're going to see, and we'll basically cover everything DC. We'll assume, Brenna, my friends, you have never heard of the DC before. We're going to cover a whole lot of AC. It's just DC at this point. We're going to talk about basic electricity, guys, tonight. Next week, we will talk about series, then parallel circuit. Then we combine the two together, and we take examples of how to analyze series and parallel circuits. And we take shortcuts of analyzing series, parallel circuits, and so forth. We will talk about, after the parallel series and the combination circuits, we talk about measurements, instruments, and then probably we'll wrap up the DC, and then move into some residential layout, and that will be the end of the semester, guys. Okay, so that's basically what we're going to be doing. So, courses for a couple of weeks of basic electricity talk, AC, DC, and parallel circuit. All right, go ahead, guys, and here's what I want you to know, Brenna, my friend, and Byron. Let me just to remind you, 03, would that be 0315? 0315, guys, that's a Tuesday. 11. I would like to schedule a makeup class, guys, 031511, so we can finish on time. So if we don't schedule that day, we will go into May, and I really want to finish us, guys, on time on April, by the end of April. So can you please write on your calendar? I don't know if Amy contacted you, but please indicate, write yourself a note that we have a class in 031511, and you'll get an invitation for this. So can green check that you received and acknowledge this, guys? Brenna, my friend, receive knowledge. Joe, just FYI, right now we are not scheduled to have a class, but if you guys remember, we lost 2 sessions. One of them we lost it because of I lost connectivity that night, and when we had a 2-hour continuing education for yourselves, the unlicensed electricians. Please write yourself a note that 031511, that's a Tuesday, that's not next Tuesday, the Tuesday after, we will be having a class. And if we do this class, we will be done at the end of April, by the end of April. So the April 26th, April 19 is the last session that we have. And Joe, my friend, I always invite you optional to session 26, April 26th, and then a review for the final. Do a review for the final, but the review for the final is optional. If you want to come, that will be great. So that's basically, we will be done by the end of April if we do this. So please write this one in your schedule, and make sure you acknowledge that. Now tonight you're going to hear Chad talking about, we're going to go down to the atomic level. We're going to go guys down to the atomic level, so you might find some of the stuff is not as exciting. But believe it or not, Joe, my friend, this is where this is the beginning of the science of electricity. So we're going to talk about atomic structure. We're going to touch on. Oh, by the way, before I go ahead, how many of you have the Dilma Standard Textbook of Electricity with you tonight? How many of you guys have this book with you? The Textbook of Electricity. This says the series I have right now is 03 here, and 3rd edition. So if you can have that one, make sure you bring this book with you. Bring another edition. This is edition 3. Now the latest edition is edition 5, I believe. The one that I have in my edition. We're using edition 3 and edition 4. So I'm going to be covering this. I'm going to be covering the atomic structure unit number 1. And go to unit number 2. We're going to cover 4 or 4 units tonight and fly through them. When we teach, guys, these at college, we cover, we spend a lot of time in each one of them. At least we cover two of every, like atomic structure. We spend just atomic structure with examples and so forth, at least 2 hours. So we're going to flip through them. So your horses, Titan you see built, and let's go atomic structure. Then we're going to go to the static electricity. Then we're going to diverge and go to magnetism. And then we're going to, after we understand the concept of electricity at the atomic level, we're going to go and introduce the most tangible major quantities that we know, which is the voltage, current, and amps. So we're going to speak a language that we all understand as electricians. So I can't emphasize, guys, go back to the atomic, and I know all of you guys have been probably in technical colleges or so, and have covered this. It's really a good review for those of you who have not taken it. For those of you who have never been in technical college, have never taken basic electricity, this chapter must read. Also talks about early history of electricity, guys. That's just if anybody's interested, IEEE guys, but really good stuff of basic electricity and the history of the science of electricity, and a lot of cool stuff. Okay, like everything else, everything started with the Greeks. God bless their hearts. So right in there, guys, it started the word electron, and look how this built it. So Greeks used the Greeks, our friends, the Greeks, our neighbors, since I grew up across the bond from them personally, so they were my neighbors. So that will be, they used to call electron the ampere, guys, electrons, and they call it electrons. When rubbed, it attracts light with objects such as dried leaves and clothes. So they rub when the ampere, it starts tracking objects, then they find the term electron on this natural phenomena. And off you went from there. Then change into electric. The derivative of electron, as you can see, means to be like ampere. So you attract objects if you are rubbed. You can attract objects. So that's where basically the whole electric started. With, as you can see, Joe, my friend, it started really with static electricity. If you rub certain objects, insulators, like as you comb your hair, I'm sure a lot of us have done that. You comb your hair and you have pieces of and it will attract that pieces of paper because of the, as we know now, because of the charges, the charges. So everything started, guys, like the ampere attracting objects is what the original electricity, which is static. So it can be charged. Then they developed it. And look how far they went, guys. How far they went. It took us until the 1800s, Joe, until the 1800s, the end 1800s, to be able to utilize electricity, even though that had been discovered hundreds and hundreds of years ago. But no, electricity was utilized in the end of the 1800s. That was okay. Then, so that material can be charged. William Gilbert discovered that the ampere is not the only material that can attract objects. Other things can attract it, and from there started the science of electricity. Electric, as it says, material that cannot be charged. So this is the thing, as it says, attract objects means you can be charged. So the concept of charging an object and discharging an object created right at this point. It took us hundreds of years to be able to utilize that concept at a commercial level where we can enjoy what mission that you and I are getting into, guys, and transmitting and receiving signals and utilizing power. Okay, that's a lesson in history. Revulsion. Then from the concept of revulsion, guys, force with which bodies, particles, or like force repel one another. Attraction, obviously, where objects attract each other, it's called attraction. Objects repel each other, particles or objects, force them to attract each other. That repulsion is completely the opposite. The force moved them apart, moved them away from each other. That's the repulsion. Why this is important when it comes about charges? As we all know, charges push each other away from each. They push away from each other. Different charges will attract each other. They attract each other. I like we will or move apart. Any questions? Any concepts? Any questions of ours so far? So with objects attracting other objects, remember, we end up with understanding why these objects are attracting other objects. So we discovered the charges. There is positive and negative charge. Charge with electricity. So what is a positive charge? Where the protons are the majority in the atom. When the protons are the majority, that particular atom becomes positive. Opposite of true. If the neutrons are the, or if the electrons, the electrons are the majority, then that particular atom becomes negatively charged, or that object becomes negatively charged. Now, guys, to how many protons you have versus how many electrons. You a positive object versus negative object. So every time you see from now on, Joe, my friend, if you see a negative guy or gal, or what you tell them, just because you have a lot of electrons on you. If you're a person who's positive, no problem. Just tell them you have a lot of protons on you. So that you can apply this socially too. That's one I told you that one. So more protons make you positive, more electrons make you the opposite, which is negative. Okay, the atomic level. Basic building block is the atom, and we know, and I'm not going to test you guys in science here. So these are the building blocks of the being and the non-being material. You are made out of blocks, which is atoms, as well as the rock and the lamp and the mouse and the screen that we're hiding right now. So building blocks is called the atom. All this is made out of a combination of atoms, as we all know. That's at least that's what they tell us. So the atoms are the building blocks. Then inside, if we slice that baby, you find electrons in it. You're gonna have the neutrons. Electrons are negatively charged. Neutrons, those are a no man land. Those guys, they don't fight. They're not negative nor positive, no charge. And the protons are the positively charged. From protons, if you guys, the periodic table, if you remember the chemistry, the periodic table, from the number of the protons, you can get a number called the atomic number of the material or element, the atomic number of the element. Table, element, periodic table, if you remember that. And then, so that's basically, you slice an atom, you're going to find electrons, neutrons, protons. And if you go in the nucleus, which is the center of the atom, we're going to have a picture here, you're going to find these sitting dancing around. The protons and neutrons are united. Here you go. So without further ado, my friends, here's your atom. If look right in this area, this is my nucleus, the center of the atom, the center of you and I, and the donkeys and the dogs and everybody else, and the horses and the rocks. Right in here, as you guys can see, are the protons and the neutrons inside the nucleus. The atoms are dancing in orbits around them. I don't know if you guys have seen all these orbits dancing around them in orbit. Dance around them in orbit. So that's basically the big concept of atom. Any questions guys about that? So you have protons and neutrons inside the nucleus, the center of the atom, and the electrons are rotating, spinning in orbit around the nucleus, which is the protons and the neutrons. Any questions? That's why did we go that far, guys? to get you in to understand how would a current become a current. How current become a current. That's why we're going down to the atomic level to justify how can we right now send 50 megawatts from Dallas, Texas to Minneapolis, Minnesota, to the atomic level. So I want to bring to your attention, guys, from an electrical point of view, our friends, the ones that we can't live without, are the electrons. The nucleus is okay, but the ones that decided our science, the science of electricity. So I want to pay attention to these electrons because the flow of them, the movement of them, the energy that moves through them will create a science that you and I then know, which is electricity. So guys, to pay attention to these orbits, especially the last orbit right here. The orbit, that's where the science of electricity starts, right at this atomic level. One more question, guys. Anybody has any questions about that? Move away from the atomic level. This is just moving, zooming down, deep into the atom. Now we're going to move away from it and go through. Then if you put a bunch of atoms together, guys, you make the elements, and that's, I'm sure you've seen that in chemistry. If you're taking chemistry, the element periodic table, and it tells you all the elements that made the exist on Earth, the substance that cannot be chemically divided into singular substance. That's what an element is. There's a periodic table of elements and so forth. Moving from the atoms into elements, making elements now, and now to understand how the nucleus is put together, guys. If you think these electrons are dancing around the nucleus, and as they move around the nucleus, there's centrifugal force that forces them away from it. At the same time, there's also a force that pushes them, attractive to the nucleus. Attractive force and repulsive force. Repulsive move them away from the nucleus, and attractive move them towards it. And thanks God that these two forces are equal. Otherwise, they'll crash right into the nucleus, and I will disappear. That maybe will be the D-Day. When the Lord is going to take us all one day, go ahead. Okay, the law of charges. On this, my friends, that we all know that if you have opposite charges, they will attract each other. God forbid you put two sides, they repel each other. We learned that one in a long ago. So the reason why it's important, guys, because especially static electricity is a big deal. Anything else about the law of charges? The law of charges. Not a big. We know it. Okay. So into some concept that's called centrifugal force. Centrifugal force. If you guys have an object spinning on another object, it will create a force that moves object that's spinning away from the object that's being spun around. So if I have my object here and I have this object and this object spinning, the further the object is spinning, the force will push this object away from the center of the spinning mechanism. So spinning object will pull away from the center of the point, and the faster you spin, the greater the force will go. So that's centrifugal force. Big deal, Joe, because when they design highways and they design all this stuff and go around curves, guys, they do take centrifugal force into consideration. So as you go, you take that curve, you're not going to be pushed away from the road and end up in a ditch. So that's a big concept in designing highways and designing a lot of stuff. Also in the balance of the universe between the stars and the earth and all this good stuff, and between the electrons and the protons. Spinning around, as you spin, it will move the force. You'll be a force that pushes you away from the center. On orbit, the electrons are doing what the electrons guys are dancing dancing around the neutrons and the protons who are in the nucleus in orbits. That's what they do. Orbits, they're orbiting the nucleus of an atomic in a circular fashion. As we said, they're dancing around it. They're dancing around the electrons. So as we saw when we were looking at them, see how they're dancing in orbits around the nucleus in different orbits. This is called orbiting the nucleus. So from law of centrifugal switch into electrons orbits, in concept, this is where the science of electricity starts. In the concept of valence electrons. Valence electrons, guys, are defined as the electrons that's found in the most outermost shell of the atom. Outermost shell of the atom. These electrons are called valence, they called valence electrons. They cannot have more than 8. Any atom cannot have more than 8. Cannot hold more than 8. And if you don't believe me, contact the scientists. That's what they're telling us. Cannot hold more than 8. This is the primary start of the science of electricity. My friends, because these 8 electrons, if I can knock one out of orbit, I have just started a current. What do you do if you have a started current and you dump that current across a load? You get yourself an electrical energy. Done. That's the science of, that's where the electricity starts. So may I get you guys to understand what a valence electron? Everybody understand what a valence electron is? The last orbit in an atom and occupies, it can no more than 8 electrons. Everybody in that one? Valence electrons. I know they're not going to be testing you on your journeyman exam on that one. I can't claim that. Okay, electron flow, my friends. So we have the valence that has no more than 8, and this is where the whole business starts. So current, the flow of electrons. So then we're moving into definition of electrical current or flow. Electrical current, as the electrons flow or move, it creates the phenomenon of the electrical current. So you have an electron. When an electron from one atom knocks the electron of another atom out of orbit, so you have one electron knocking another electron out of orbit, you get that baby moving and get yourself an electrical current. I'm not telling you it's going to be 2000 amps now, but that's kind of the source, the source of the science of that 2000 amp switch gear and the 4000 amp switchboard that we install all the time. Last orbit, the valence orbit, one electron kicks or knocks another electron out of orbit. The second electron starts moving. It creates the energy that's called electricity. That's called electricity. Not every atom can be a conductor to electricity, guys. So if you guys remember, the valence can house no more than 8. If you went and saturated them, Joe, you put in the valence 8, 7 to 8, you just created your T, H, and insulation. You not conductor. You just created an insulation. That's what insulators are a big deal. So the material that makes the insulators, the rubber, the wood, and all these very insulating, non-conductive materials, when you use it at the atomic level, you're supposed to find 7 to 8 electrons in the last orbit of the atoms that makes that substance or that material. And Joe, if you don't believe me, you're going to go tonight and test it, right? Just go, you would, and try go slice it down into atoms, and you're going to find that 7 to 18 valence electrons. Huh? That would be a joke. Okay, that's insulators, as we know, because there's so many of them, knocking any one of them out of orbit. So because there's so many, they're united. You know, gather 7 to 8 of them filling the whole orbit. So an intruder to come and knock one of them out of orbit is not going to happen. So what does that not going to happen? Now you got yourself an insulator, which is a plastic, a glass, or a wood. And I know, guys, Joe, my friend, and Matthew, insulators are as important as conductive material, right? We realize as a human being the insulating material as much as we like plastic or rubber, as much as we utilize the conductive material as copper and aluminum. Because without insulation, good luck pulling your conductors through rigid or PVC or AMT or anywhere else. So that's what created the insulators. Any question, guys, about insulators? How can a material become an insulator? Just 7 to 8, there are so many of them united, you can't knock them out of orbit. Semiconductors, now guys remember, you can get from 0 all the way to 8 in the last orbit. Now you get 7 to 8, you're an insulator. If you 4 right in the middle, 4 electrons in the last orbit for the valence electron, you yourself a semiconductor. I'm not going to convince you, Matthew, that the semiconductor are why you and I are engaged in this learning activity right now, because of the semiconductors, thank God. Because the electronics, the source or the mother of digital world that we enjoy right now, and you can Skype through your iPhone and talk to people across the globe from your iPhone, as we know. So that's because of the start, the semiconductors, the chips and all this good stuff. So the smarter than Chad utilize the insulators to insulate material, the semiconductor to create the electronic and digital world that we are enjoying. And I'm going to tell you that also the conductive material or the conductors are utilized in our industry to carry power from point A to point B. So their problem, these guys, when you heat them, the resistance decreases. That's them, and it is the source of all the solid state, the electronic, and the digital world. So we insulators, 7, 8. We have semiconductors, 4. And what that says, now if you have a conductor, we have it here. If you have 1 to 2 to 3 electrons, especially 1, 2, you have a conductor. You got yourself a Cu, cover, or aluminum. Right? You got 1 or 2. Why 1 and 2? Because if you have 1 or 2 electrons, I can easily bring and knock that electron out of orbit and get that snowball rolling, which is called the electrical current. The electrical current. So with the electrons, the conductive material, the conductor is, you have 1, 2, 3 electrons. If you became 4, it's a semiconductor. All the way to 8, it's insulator. Molecules. The molecules, the smallest part of a compound. You have a compound, without getting to chemistry now. Now, moved one step higher. We grab multiple atoms together to make a molecule. And multiple molecules, guys, make a compound. Multiple compounds there make your friend Chad Kennedy. My head right here, couple of compounds make you and the monkeys and the screen and everything else. So these are from the atom to molecules to the compounds to us. There's a fifth in between. So example, water. So the water is a compound. It's made out of the 2 hydrogens and 1 atom. 2 H2, 2 hydrogen, and H2O. Two atoms of hydrogen, 1 atom of oxygen. Any question guys about this? That makes the molecule or compound, which is H2O. H2O is a couple of C's, carbon, and you made your friend Chad Kennedy. We're sitting in front of you. Okay. Any questions before I give you a little poll here so you can test your science information? Any questions? Let's test your science information. And again, you do this one time, guys, and you don't get back to it. I'm going to go ahead and I have 10 questions. I have how long? Let's give 6 minutes here and go ahead and start, my friends. A quick review of what we have went through. One will talk about how large and how heavy the protons compared to the electrons, and a couple of comparisons. Okay. 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 Almost end. All right. Oh, so that was a good review of the atomic theory of electricity down to the atomic level. So we wait for this to a second, guys. Okay, this one, guys, we just dived in. I want to share the answers with you. Dived in and moved. We went down all the way to the atomic. We visited the protons, the electrons, and the neutrons, and we discovered that we have electricity because the last orbit that can host no more than 8 electrons, it has smaller electrons added 1, 2, and 3. One of these electrons can be knocked out of orbit to create that ball of snowball, which is called the flow of electricity. So, also the bottom, guys, they believe that also the protons and the neutrons are made out of quartz, little pieces. That was a new. So there's a couple of things, guys, but the most important thing is really the last orbit that defines what an insulator is, what a conductor is, and what a semiconductor is. Any questions, guys, about what we covered? Any questions? Hop in for Chad. Make sure that with me. Now we're going to move. Now we zoomed right into the atom, the nucleus, the electrons. We covered why we have electricity because of that literally knocked out of orbit. Now we're going to go zoom out and look at it from a 33,000 foot level into the electrical quantities and into Ohm's law, into electrical quantities and into Ohm's law. And that, guys, will be chapter 2 in your electrical unit. So here's what I suggest, Matthew. If you have never read this book, guys, it's really nice. There's a lot of stuff in this book that we just touching on because of we just trying to go over through them. Okay, moving on now to a concept that's Coulomb. The Coulomb, friend, is the quantity measured of electrons. So this weekend, Joe, when you go to the bar, my friend, and visit your friends, tell them that you know now that 1 Coulomb is 6 raised to the power 18. What does that mean? It means 6 and 18 zeros. Here's the 3, and you just keep going all the way to 18 zeros in the front of it. That's much more than national debt of the nation of America. That all these numbers together, guys, make one. Electrons make 1 Coulomb. Okay, Chad, because now remember we went down from 1 electron moving into a group of them moving as a pack called Coulomb. We can create the charge, guys. The charge is measured in Coulomb. So the force of electrostatic attraction or repulsion is directly proportional to the product of the charges and inversely proportional to the square of the distance. Well, let's go, and this is the science. So we know now we have grouped all these electrons in big lump sums. So I have HU, a positive charge, and another positive charge, and I need to find the force that pulls them away from each other because they're too positive. Let's assume the distance between these two charges are, and the reason why I want to put this one because I was tortured, Matthew, with this equation when I was in college like you guys. So I have to torture you tonight with one of them. If you want to find the force, guys, that's what they taught us when we were in the engineering school. You find the force between these two, no problem, Chad. You take an M is the multiplier divided and take the Q, the value of Q1, multiply it by the value of Q2, so that will be Q1, this will be Q2, Q1 by Q2, and divide it by the distance squared, divided by the distance squared. Okay, about all this, Chad, the force between these two between charges is proportional to the value of the charge and inversely proportional to the distance between them. That means, Chad, it means the further away these charges move, the further away, the smaller the force that pulls them from each other. The closer to each other, the more powerful the force at the distance. And of course, the more charges we have 5 charges, 10 charges, 25,000 charges. The more charges we have, the more attracted, in this case, the more the force will pull them away from each other. And that's what they call it, the Coulomb law. The Coulomb law in a mathematical equation. So the force is inversely proportional. The smaller the force from the distance, and directly proportional to the value of the charge, meaning the more charges, the more the force is. That's basically what the Coulomb is. Now, who cares about the Coulomb? So if you guys look what they did, they grouped a bunch of electrons together to make a Coulomb, okay? And then now we're going to be moving in this pack of columns. Instead of one electron, we're moving in pack of columns. So 1 column per second, so 1 column moving through per second here, of the amount of electricity that flows through a circuit. Now we are moving, so we define it. We start from 1 electron, Brenna, my friend, group it with another 6, in front of it 8 zeros, electron, okay? Trillion, whatever. And if those guys moving as a pack through one cover conductor number 14, that make 1 second, that will make 1 amp. That will make 1 amp. I bet none of you guys will ever think of this when you're measuring that 15 amp in the circuit. Column and electrons would never cross your mind, huh? So of flow through a wire when one column flows past a point in 1 second. That's how the electron, Brenna, is connected to the amp that we know. We went from electron into a pack of electrons that's called Coulomb, into a pack moving together at the speed of light as they move per second. That's my 1 amp that I can dump across a 120 light, and I get myself 120 watt lamp glowing, if that makes sense. Any question, guys, about the amp definition? That's not enough, my friend. I'm going to torture you with another formula that I've been tortured with when I was in college. They define it as dq, and I assume none of you have done calculus. dq is over dt. That in an engineering term. Now I'm sure a lot of you are yelling at me and yakking here. They define as the current. So in the d is a change. The change in the charge divided by the change in the time. Now we are talking calculus, and let's move on. Any question, guys? Any question, my friends? Now we went from the electrons into the columns, into the amps. Now we entered the electron theory. We entered the electron theory. Other theories, guys, about the flow of these electrons. The electronic guys, because they don't like the electrical guys, oh, by the way, the electrons move. Here's how it states. The electrons are negatively charged and flows from the positive to the most negative. Here's the positive, here's the negative, and the current goes this way. The electron theory, the people who do electronics guys probably learn how to do it. So let's just use a battery, for example. Here's my battery, here's my positive, here's my negative, and here's a nice light. I'm going to go dump the battery across this light. Okay, so here's my current. I went from the positive to the light. I want to go from the negative to the light. Okay, and now, if depending upon which theory you use, if you're using the electronic theory right here, the current is going from the negative, the current moving this way, from the most negative to the most positive, this direction. Okay, so negative parts, current flows from the most negative point to the most positive point. Now, theory is called conventional theory. One theory is concerning electrons, the state that the current flows from the most positive to the most negative point. It's the opposite. The opposite. Who cares, Chad? It doesn't matter, guys. The other one says, no, by the way, the current goes from this way, exactly the opposite, to the other way, right? So that's opposite. So these are two conventional guys. Either one of them would work, Jacob. But here is one thing there is no doubt about. One thing, no doubt about. The power goes from this direction to this direction. So, guys, is the power. Meaning, if I have 1 amp coming out here, 1 amp, and if the voltage is 12 volts, it will be consuming 1 times 12, and lamp will be running at 12 watts. There's no doubt about it. The current going positive to negative or negative to positive, these are convention. It's like if you go to England, they drive on the wrong side of the road. They drive on the left side of the road. We, as 80% of them being, drive on the right side of the road. We drive. The outcome is the same. You can drive from your house to your work and to your shopping, and you can do all your work. That's what the outcome is, the watts. But you're on the right side of the road or the left side of the road, who cares? So about this, so that's basically the especially the DC. When we get to the AC, well, the whole positive negative disappears because AC is alternating. The positive changes constantly and the negative, right? So that's only in the DC theory where you're positive and you're negative. And power industry, Matthew, they use the conventional one. There you go, the conventional. This one is most used in power industry. Electronic industry, obviously the electron theory is the most, which is positive versus positive negative. Any questions, my friends? I don't want you guys, Jacob, my friends, to get confused now and say, well, Chad, this to make up their mind. It doesn't matter. The power always go one direction, Joe, from the source into the sink, in load, from the source into the load, regardless of the convention of the current. Regardless of the current, the power always goes from the source to the load. That stays constant in any theory. That's IP power. The power. Any questions about the electron theory versus the conventional theory? Again, in our industry, we use a lot the conventional theory, where it goes positive, the most positive to the most negative. Basically, the couple of nice pictures, guys, in page 55 that goes all theory. Electron theory, the most negative to the most positive. Okay, but the stays always the same. Okay, moving on. I know you're doing a break. I'll give you guys a break in a second here. Speed of the current rate, the speed of the current, guys, is is, let me use a different color here. The speed of the current determines the current itself, so the at which the electrons are moving, which is, where is that one? There you go. Okay. One more time. Okay, so here's the rate of the flow of electrons is called the current. The current is amps. So it is a single electron moves at, look at this, a single electron moves 3 inches per hour at a 1 amp of flow electron, at 1 amp flow electron. Interesting, that one. Whether it's a DC or AC or any other radio frequency system. So a single electron moves at a rate of 3 inches per hour, 1 amp of flow. 3 inches per hour, you create a 1 amp flow. Anything, guys? Any question, my friends? Any questions? Okay, we move into, so we went, guys, into the atom. We got that valence electrons. We defined what insulators and what conductors and what conductors are. And we grabbed a pack of electrons. We call them the columns. And we say as the column moves through the line in a conductor, creates the current. And we established the concept of the current. And then we talked about the conventional and the electronic theory about the current flow, positive to negative or negative to positive. And we decided then that it doesn't matter how you flow, you drive on the right side of the road or the left side of the road, as long as you make your mind, the outcome is the same. You will reach your house and you reach your job safe, depending on which convention you use, if everybody's follow the same convention. Safe means everybody's going to have to drive on the right or the left. Into the basic electrical, guys, we have the closed circuit, short circuit, and the grounded circuit. There are a couple of circuits, as we know, short circuit and grounded circuit. These are the situation where basic electrical complete circuits that you, so short circuit, and you have the grounded circuit, and you have the or the neutral, the grounded circuit, you have neutral, and you have the closed circuit. A couple of, here's my value here, positive, just negative, and I grab this one. Here's my switch here. I close my switch and then grab it to the light. This is my circuit, basically the closed circuit. If I want to short this baby, grab these two and shunt them together here. You shorted them. The grounded circuit, guys, you can grab another conductor, ground it over here, or you grab one conductor in alternating and ground that conductor, intentionally or unintentional, intentional or unintentional grounding of conductor. So that will get you a closed circuit, a short circuit, or a ground fault, or a grounded circuit. Again, I don't want to talk about the grounded conductor, guys, because sometimes intentionally we ground the conductor, sometimes it's a ground fault. Move us, guys, into the concept of voltage. Now moving from that level into more tangible stuff. The voltage is the amount of potential necessary to cause one column. Remember that pack of electrons moving together to produce 1 joule of work. So it's the force that can take a pack of column electrons, they make an amount of joule of work. Now we're still not saying it's the difference. The potential, guys, that push the power to go from point A to point B. Okay, also electromotive force. It's the force that pushes the current through the circuit. Very interesting. That's the potential difference. I always describe the voltage, guys, as if you have a water flow, you will never hit that water flow, and these are 100 feet. If you have 100 feet, difference in elevation, and you have the water moving in here, then you have a water flow. The reason we have to have water flow is because of the difference in elevation. The difference in elevation is like the difference in voltage. So we have 2-4 system. 2-4 system. It's as if you have volts, as if you have an elevation of 240 volts. There is my 240 feet. that will allow the current to go and you have a waterfall. Otherwise, you don't have elevation. Would you ever be having a waterfall? You would never have a waterfall without elevation. The same thing, you would never have a current, electrical current, without a voltage. You've got to have a voltage. Voltage, not just a voltage difference. Look, the voltage here, the elevation here is 2 feet. The elevation here is 0. So look, at elevation here is the elevation at this point is 0. The elevation at this point is 110. That's what they call it, the potential difference or voltage difference. If are the same potential, guys, look at that. If this is sitting also at 100, you will never, the water will continue going this way. You will never have a water flow. I mean, waterfall. And guys, about the waterfall and voltage. The voltage is the source that pushes the current to go through the conductor. Current to go to my conductor. If I told you, if somebody tell you guys, I want to create a unique system, you tell them, oh, no problem. I want to make a voltage of 100 and let's make a smart Alex 73 volt system. Can I make a 173 volt system? Yes. And a lamp at 173 volts, no problem. Bring it on. It's conventional. So what you have to do is just create yourself, if it's DC, for example, let's say a DC system. So start adding your batteries. Start batteries until you get to 174 volts. So add batteries in series, adding your batteries in series, adding your batteries in series, 24, until you get yourself a voltage, that voltage, and then you tie it to your equipment. So you've got yourself a DC voltage of 173 volts. If it's an AC voltage, what they do is they create coils, guys. Create yourself a coil. How many windings you do until you get yourself 173 volts on the side. Other side, you have, of course, you have to use the conventional voltages. So I'm going to have a 480 from this side. So one side 480, the other side is 1V, and I created myself a voltage of 73 voltage source. Any question, guys, about voltage source? If you have a voltage source, you would have a circuit. If you don't have a voltage source, the current will never flow. So the key point, guys, the source is like a pump through the pipe. If you have a water and you have a pipe and you don't have a pump, the water will never go up the hill without having pump, right? On the hill, yes. Up the hill, no. You need to pump that water upward. That's where the voltage comes handy. Okay, the voltage. Then as the current, these pack of columns, guys, move into the conductor, it will carry resistance. That's called the resistance R. It's rated as the amount of resistance that the current will counter, and it goes through the conductor. So 1 ohm in the amount of resistance that 1 amp. Look at that. 1 ohm is 1 ohm. Is actually 1 amp. 1 amp will flow. It's a 1 the resistance that 1 amp is going to encounter if it's powered, pushed, driven, utilized by 1 voltage. So voltage pushing 1 amp, that amp will encounter a resistance of 1 ohm. Okay, so my voltage 1. Here's my 1 amp here. My 1 amp. Here's my 1 ohm, and here's my 1 volt. So if 1 volt equivalent to a push, or push with 1 volt, it will push 1 amp if the distance is 1 ohm. Or if it's pushing 1 amp, it will receive a resistance of 1 ohm. And before we the concept of the power, and that will be the last concept here. Any questions? So we're moving towards Ohm's law, my friend. So you take the current You take current and the voltage, and you get yourself a power. The power that is being used in the circuit is called the watt, the amount of power that is used in the circuit. So this circuit, my friend, if you take the current, here's my current I, multiply that current by the voltage that's coming, the pusher, so you get the voltage, and you multiply by the current I, you get the concept of the power, volt, amp, or watt. Is the single most important concept, Joe, because the current go right to left or left to right, no problem in DC, but the power goes only one direction. The power is always going to go one direction, from the source into the load, from the source into the load. So I'm going to steal some power from this battery and go cook this power to fry my eggs here, to fry eggs, to fry my hamburger, or whatever. The power always going from one direction, from the power source into the load, regardless of the amps. Power is measured in a couple of inches. Horsepower, is we use it all the time. Our friends, the mechanical engineers, use the joule and the PTUs. Not commonly used in the electrical industry, but the most commonly used for power in the electrical industry is the horsepower and the watt, and of course the volt amp, which is a function of the power factor. Okay, let me guys go get you a quick break here. What time is it? It's 7:16. 7:21 is be good. So 7. Let's keep 7:21. Go get yourself something to drink. see, guys, if I can get you to join me. You can check in, my friends. I'll be very thankful. Okay, we moved, guys, from the electrons into the columns, into the current, into the concept of an electrical circuit that has a voltage, a current, and a resistor. Now, this is a very interesting topic, as I said. We're moving into the tangible stuff, which is the Ohm's law. Now, all of us probably know Ohm's law. The most important thing of Ohm's law is the voltage, the electromotive. This is the driver of the whole electrical system. You've got to have the potential difference, the electromotive force, the force that moves the current through the conductor. The thing is that when you have the voltage, you need a current. That current is going to carry the energy from point A to point B with it. And as the current moves, it's going to encounter a resistance that will be measured in R. This is the most important concept, which is Ohm's law. So as the current goes up, the voltage goes up. Granted, the resistor is down, guys. As the resistor goes up, so to increase the current, you increase the voltage. Increase the voltage, increase the current for the same resistance. About Ohm's law? Any question about Ohm's law? My friend, as we move through and we start analyzing parallel series circuits, if you don't know Ohm's law, you're lost. Get into parallel series circuit. And some of you might say, well, Chad, why should I know parallel series circuit? Because you need to pass your journeyman exam, right? So you know parallel series circuits, you need to pass your journeyman exam. If not anything else. Okay, out of the Ohm's law, guys, out of Ohm's law, this is called the Ohm's law. There's another law that's called the power law, which is P equal, or are they using it in E? They use E. So let's just use E. No, E is the power. They use P. Okay, let's use P equal E squared, not E squared, E times I. This concept is very powerful. This is telling you that if you want to increase the amount of power, because the city of Minneapolis needs to add more loads to the city, or the city of Bloomington, then two options. Are you to increase the voltage or increase the current? If you increase the current, Joe, you need to increase the conductor size, as we all know. But if you maintain the same conductor size, you might have to increase the voltage. That's the concept they use for utilities, guys. When they outgrow a transmission line, what they do, they raise the voltage from 13.8, from say 100 volts into 13,800 volts. That, of course, they have to change some insulation, some conductors in the process. But at change, they can triple or quadruple, quadruple as a matter of fact, quadruple the amount of power that the system has. Okay, so this is there are two laws. Law number one is the Ohm's law. Number two is the power law. From these two, guys, you can create 12 more formulas. And I'm going to do one formula for you. And I trust that you're not going to sleep Matthew tonight until you get the rest of them. So say E, guys, here's my E, equal the voltage equal the current I times the resistor. Okay? Let's say I want to go and let's just say they come up with this one here. No, I come up with this one. I need P and R, a relationship between E, P, and R. Okay, so that's what I'm going to derive. Then I need the power, which is P, equal I times E. Okay? From these formulas, I need, guys, to keep the following. Look what I'm going to be keeping. I'm going to be keeping the E in the formula, so I don't want to get rid of it because E is here. I have the P, so what I do, I need to keep a P, and I want to keep the R. Whatever I do, I need to keep the R. So doing this, guys, you know the only thing I can eliminate is the I. They want to eliminate the I. So look at that. Now this is the I want to eliminate. I want to eliminate the I. Okay. Here's what I do, guys, for the second formula. I'm going to solve the second formula as I equal P over, right? Everybody knows how I flip the formula. So P equals I times E. You swing the E to the other side and put it under P, and then I stays by itself. So P equals I, P over I. So then you take this I, guys, and you substitute I from of the second formula in the I of the first formula. But this is called your first formula, and this is my second formula. Here's what you're going to end up, guys. You have the E, and instead of I, I'm going to go have a P, E. You see that? P over E. Multiply. Don't forget that P has to be multiplied by R. I need to solve for E, though. So if you do cross multiplication, do you remember how we did cross multiplication? Top with bottom with top. So that will get you an E squared P times R. You guys don't hate me now because of this. And then to make E by itself, we take the square root of both sides. Remember how we did the math? Square root of sides. The square root of E squared is E, and the second part would become P R. The came of the E equals the square root of PR. Now, as usual, I will not memorize all these formulas. There's no way I can memorize these formulas. So the only thing you need to know, really, the only thing you need to know is the rules. In here, 1 and formula 2, and how to manipulate them, guys, to get you whatever you want to do. Okay, a few things probably you will remember all the time from these. The rule 1 here, guys. See, this one is easy to remember because that's the Ohm's law, right? Can't go to town without it. Ohm's law. This also we can't go out. This you have to memorize. That's the power law. These are the only two you need to remember. These are the only two out of all math that you need to remember, memorize. So that's and you can derive the rest of them, guys, easily. A couple of ones I found them handy. ER, that's a really nice concept to memorize. E squared over R is another really nice concept to memorize. So these are I like because the application. Other than that, you need to memorize anything. You can derive any one of them exactly like I did. Questions? Question is about the Ohm's. That's what we call the Ohm's wheel. The power and the Ohm's wheel. So formula, I can solve for any, this is a DC, guys, which applies for the most part to DC with some modification. Any question of my friend Dan? Ross? No? I guess respond when I ask you, please. So that's basically, pick a formula based on the power law and based on the Ohm's law. You don't understand these two rules. This one, I teach Jacob, and I teach the exam prep for apprentices like yourself. And there are a few questions about the Ohm's law in a direct way on your exam. If you don't understand these two, good luck getting these couple of questions about parallel series circuit. Because even parallel series circuit, guys, depends on you understanding the Ohm's law, power law. You're going to be next week when we start analyzing the circuit. Until you find the power across this resistor, I assume that you know that the power is E times I. And as you find the resistor, I assume that you know that the Ohm's law is I times R. So please, I can't emphasize the importance of memorizing and understanding these two formulas And using the rest of this, you write it, or you just, if you have it in front of you, you can pick the right formula for the right application. Electrical industry, guys. Let me just take a quick example here. Let's say we have a 20. Let's say we have a voltage system, just to get you an idea. Resistor. Give an example. An R, and here let's choose 120 volt here, and an R, and I know the current that's going through it is 10 amps. That's ohms, guys. 10 amps going through resistor that's powered from 120 volts. Find R. The question is find R. I want to. If you get the ohm law, E equals R phi, right? Since I solve for R, you put one R in one side. Anything multiplied by R will be divided on the other side, or the other will be divided by it. So that will make it look like this. Because I took this and I wing it all the way to the other side, and I put it at the bottom, right here. Because I need to isolate R. So, long story short, then R equals, guys, what's the voltage? 120. Divide the current 10. R actually is 12 ohms. Is the 12 ohms. Piece, Chad. Now, the second thing I want to ask you is go find the power. How much power this is going to consume? How much power this R is going to consume? Okay, no problem, Chad. P equal what? Equal the voltage multiplied by the current. Okay, voltage, which current? The current right here, with also 10 amps, right? And this voltage right here, voltage, which also 120 volts, because there's no other MP. Can you guys see? You guys see the voltage from here across is as the voltage across the load. So piece of cake, you're going to take your 120 and it by 10 and do a 1200 volt amp. No, 1200 volt amp. That will give 1200 volt amp. Question about this? Question, Matthew, my friend, Ross? Any questions? So that's how to use the Ohm's law. Very simple. Now, guys, when we start using them, we're going to be using them in more than one resistor, in series, and also more than one resistor in parallel, and then we're going to do the combo of series and parallel. So but you just understand the Ohm's law, which is baby here, and law. From there, you are good to go for a lot of calculation. You're good for a lot of calculation. Oh, then we have known the Ohm's law and the power law, because are very proficient in Ohm's law and the power law. We're going to go into a couple of acronyms that we use to describe the power and the voltage. A couple of them, guys, very common in our industry is the K. The K, we can, when in the power industry, guys, we don't say 3000, we never say 3000 or 1000 volt amp for transformers. That's not really used at all. But if I have a 30,000, you put 30,000 K V and A. That's the application. That's a transformer 30 kVA. Okay, medium voltage industry, guys, if used voltages that's 13.8 kVA. So it's used with voltage. This is 15,800 volts for the distribution system for the K for the distribution system. So that's where a good application of K is used. And is used also with generators and transformers. If you're lucky enough in your life, probably you will encounter a 20 meg volt amp transformer. It's a big boy, 20 meg volt amp transformer, or 2 megawatt generator. Megawatt generator, turbine, or diesel. So the meg, guys, is a million, and the K, of course, as you can see, the meg is a million, and K is 1,000. 1,000. We encounter these definitely. We use them a lot in the telecommunication gigahertz. Gigahertz, which is basically 100,000 million or trillion. But these are the common, guys. Milliamp, use it in milliamp, not a whole lot. This is 1,000th of an amp is milliamp. Micro, if you are dealing with micro, we use it with capacitors, guys. You're going to see a lot with microfarads, micro, pico. Ooh, that's getting deeper into the electronics. For the most part, micro is the small unit that we use, and we use microfarads when we deal with capacitors. And guys, about these multipliers, any questions, multipliers, Ross, my friend? Any? With this, I'm going to get you to chew on this 17.5 pull and see what we can pull through. I have 4. I'm going to give you, my friends. Okay, 8 is good. 8 minutes to chew on that one. Okay, go ahead, guys, and start poll number 2, please. Review of the ohms and the amps and power and so forth. still have some calculations with it. That's really interesting. Okay, almost done, guys. Here. All right. One second. All right. So I know there's a lot of it with calculations, so I'm going to share this one. I don't have time to no problem, Juan. It will take some time, but because of time, I have to keep moving. One of the things, guys, I want to remind you, when you have an algebraic equation that these two in front of you, if I give you any two, if I give you I and E, you should be able to find P. Or if I give you P and I, you should be able to find I, and E, you should be able to find E. Or if I give any two, or if I give you I right here and I give you P, you should be able to find E. So I can't emphasize, guys, when you have an algebraic equation of three variables, if they give you two, you can find the third. The thing here, if E is given and I is given, you can easily find R. If R is given and E is given, you can find I. Or if I is given and R is given, you can find E. So I can't emphasize, for your own sake, guys, if you pass the general exam, make sure you know how to manipulate these two formulas to find. For example, I can find three formulas out of this formula. I can find three formulas out of these formulas. And if I combine the two together, I can create 12 formulas. 12 formulas, as you guys can see in the Ohm's wheel. Formula. Okay, question guys about the quiz? Any question? Any question, my friends? Any questions? How about an expert chat? Make sure, or I know you were not able to finish all of it, but that's basically, please, if I have a request from you guys, just please go back and review these and make sure you basically give different series P and E and solve for them. Because this week when we move into the series circuit, I'm going to expect you guys to know how to use these two on multiple resistors. Otherwise, lost. Really, we get into the parallel series circuit and you're completely lost. Okay, moving into static electricity. Static electricity, guys, is not moving. It's the name indicates it's static. Nothing is moving, static. So electricity, electrons are not moving, they are charged. So the current is a charge. The only difference between static electricity and the other electricity or dynamic electricity, static electricity, guys, it's charge. Dynamic electricity is a moving charge, while static electricity is a standstill charge. Doesn't move. Okay, so electrostatic charges build up on insulator material, and I'm sure you guys have seen a lot of insulators. Charges will build up and then you discharge. They have the term discharge. Okay. Keep working with my friends. Thank you. So then you charge and discharge. That's what they call it. It's not a current, it's a charge. And you remove the charge, that's a discharge concept. When you have a charge, that's a charge concept, charge to discharge. Oh, charging can be either positive, you can add a positive as adding electrons, or negative as in a positive as in removing electrons, or negative as in adding electrons. Charge on the objects and on the materials that use. So basically what the whole static electricity is based on electrons, which creates charge, but the charges are not moving, they stand still. The man Chad created that tool that they call Electroscope, so you can test if the equipment are charged positively or charged negatively. There's a whole industry, Matthew, that depends on the static electricity. Printing industry is one example of that. Print industry, a big example of depending upon the charge and discharge. And this, guys, is chapter 3. You can see, so that static electricity also, guys, is in nature and lightning, as we can see. The positive, as you can see, his positive and his negative. Negative going to the positive, discharge, you got yourself a lightning. You have a negative, you have a positive, negative going to visit the positive, that's the lightning, cloud to cloud. You have also, you can negative house to cloud, positive, negative. So these are all discharge current. Lightning is a discharge, not current. Now, Matthew, my friend, you can chance, well, how I can capture that discharge and create a current from it? No problem. Like in batteries, you can charge the batteries and release that charge as a current. No problem. Charge and a current. Static electricity, guys, you probably have seen when you get into the automobile, they move through the dry air. You get out of your automobile and you touch the gas pump and you get that little shock, or you touch somebody else. I'm sure all of us have been there, very nuisance. As you walk across the carpet, guys, and you grab the knob of a metallic knob of a door, and you get that little dab, or you touch a fellow human being or anything else, and you get that little dab and noise and that little spark. That's discharge, negative to positive charges, basically. Actually, also on the clothes dryers, and you take them out of your dryers. So these are nuisance ones. The ones that we love and dear to our heart, not our industry, other industries, is painting. They use the spray painting. They use the concept of charge and discharge, and so they can negatively charge paint, the object, and positively charge the paint. And if your object is right here, negatively charged and you're or positively charged, and your paint, the paint you want to spray at, is positively charged. Now you shoot this one on the object, and you guess what? You get yourself a negatively charged attached to a positively charged object. Negative charge paint attached to the positively charged object. Long story short, you can use the concept for paint. The same thing for machines. And the examples in your book, the way you use the paint. So you have object to be painted receive a negative charge. Wire used to charge the particles of paint. So you throw into two positive charges. The object is negatively charged, and then positive negative attract each other. So you got yourself a painted object. Page 90, guys, they also use it in the copy machine. So letters, and they make the letters stick on copies by positively and negatively charged objects. So that's basically two major industries that can use the static electricity. In the industry, not a whole lot of application on the power electrical industry that I know of. So not really a whole lot of applications in the power industry, as I said. A lot of application in any other industries. So oscilloscope, electroscope, guys, would be about the electroscope. What do with the electroscope here? They test if something is positively charged or negatively charged. The first thing do, guys, is they charge it. They charge it. So say we charged it with negative here. So with negative, these leaves, it's made of two leaves. If charge it with negative, these two leaves, guys, they open, they move away from it. So the key point is always to charge this scope with a known charge. Then you go grab another object. Here's an object, and on this object, I want to find what is the charge in this object. Okay, so what's the charge in this object? That object is negatively charged. Say if that object was negatively charged, these will move apart from each other. Move apart from each other. These will move apart because the charges are going to go down, 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 and add to the negative charges here. So if they move apart, then the new object is negatively charged. If the object is positively charged, then these two will move closer to each other. Move closer to each other. This means the object is positively charged. And now they discover, the smarter than Chad, if object is negatively charged or positively charged with this electroscope. Any questions about that? The electroscope, would that be asking you? I believe in a poll, if I remember that right. Okay, I have another poll for you. These are 10. I'm going to give you 5 minutes. Only have a few of them tonight. Let's start this one, guys. 5 polls about static electricity. Know it exists. Know that it's nuisance. And know that there are useful applications for static electricity, as in paint and print. Paint and print. So that you make the letters stick on the paper by positive and negative charge. Charge the letters with positively charge the paper, and negatively charge the paint or the print. So it sticks, the letter sticks on the paper. Okay, start that one. Okay. So it might take you a few longer than normal. Okay. Sincere apology if you will not get to finish, but I just moving it because of the timing. Okay, so I had the chance, guys, to look at these. A couple of things I wanna mention as section. You have lightning rods of lightning resistors. That's just FYI. I thought we didn't mention this. For fourth, guys, how can an object be? How can I'm going to go share more with you. How can an object be positively charged? By removing electrons from it. How can it be negatively charged? By adding electrons from it. So that can make an object positively charged or negatively charged. I'm just looking at your answers here. So that's basically the most important thing. Any question, guys? Any question before we move into magnetism? Question? Any? How about an extra chat? Make sure that you guys are with me. Now, magnetism. Magnetism, guys, is oh boy. The most important things that happen to electricity is the match between electricity and magnetism. And you're going to see why in a second here. So talk about magnetism, guys. The discoverers, look at that. Who else other than the Greeks? They haven't left anything for any other civilizations to discover. They discovered everything early on, guys. 100,000 years ago. They discovered the force that produces most electrical power in the world. This is the most important thing. Because of magnetism, electromagnetism force, guys, we can generate and generate and utilize power and convert power from electrical power into mechanical power. That's it. the concept of electromagnetism. That's a huge, huge concept in the electrical industry. Let's go down to the beginning, like we did get into the current. We went down into the electron, and we grouped an electron with a pack of electrons, and we call them columns. And we move the columns, and we call these columns an amp. We sat these columns sitting and not moving, and we call them a charge. If you guys remember, we call that charge is static. Same for magnets, guys. It started with the lodestones. A lodestone, narrow magnet, align themselves north-south. So that's basically naturally magnetized material. Always align themselves with north-south pole. Earth itself contains magnets as we go north, and the magnetic poles of the Earth are the opposite of its natural pole. So the south is north and the north is south, I guess. So that's the most important thing. Magnets do not require any power. This is called permanent magnets. Magnets that are naturally material that's magnetized naturally without any force of magnetism. Why does a material become a magnet? Another material can't be a magnet. Only three substances be magnets: the iron, nickels, and cobalt. And here they can become magnets, guys. What they do, remember these electrons that's rotating, dancing around the nucleus? If they dance and rotate, spin around their center, so you have the electrons, right? Is my proton, and you have electron right in here, and only the electron is moving, guys, but it's also spinning on its center, so it's spinning. So the spinning mechanism, believe it or not, they're telling us that creates the phenomenon called magnets. Domain is range, how far that magnet can reach, and magnetic molecules are really nicely organized magnets, guys. So the material that's magnetized is nicely adjusted molecules, positive, negative, and positive, negative. All these molecules are nicely adjusted. So, if you have a naturally magnetized material, you're going to have electrons in orbits that are rotating on the protons and the neutrons in the nucleus, and at the same time, they're spinning around their center. They're spinning. And I have it, guys, in page 97 has a really nice example of the spinning. Electrons generally spin in opposite directions. So if they're spinning and they according to their spinning, guys, they create the material electron spin patterns. So they create the material that we call magnets. The materials from a magnetic point of view is divided into three. Magnets, materials that can be easily magnetized. Para, it's not easily, but you still magnetizing. Diagram, good luck. It can't be magnetized. No matter what you do, you can't magnetize these materials. So from a magnetic point of view, you can split all material in the world into one you can easily magnetize, one you cannot easily magnetize, and one you can't magnetize no matter what you do. Okay, so why this is important, guys? Because it's when we build the transformers, when we build the generators, what type of material to use so I can create a better electromagnet. Okay, magnetic lines, guys. If you have a magnet, and you have your north and you have your south, there will be lines going around from north to south. These are magnetic force. They call magnetic lines force. The magnetic lines of flux will build each other and never cross north and south direction. So a basic of magnetism, unlike poles, exactly like charges, guys. Remember the charges? Unlike poles attract and like poles repel. So if you have a north pole here, pole, what do you get? You guys have seen that electromagnets. They pull each other way the opposite is true. If a north and a south, this is my south, and they will attract each other. Exactly like the charges. Positive charges, like charges attract each other, and like charges repel each other. The same thing. Unlike poles at each other, and like poles repel each other. Anything else about the basic rule of magnetism? And about the basic rule of magnetism? They force Jacob, my friend, with flux. They call it flux, which is magnetic lines. So I have a magnet right sitting in here. Around the magnet, there will be curves going on it, and these are the magnetic force lines. These are the push or attract things away or to the magnet, Now, this is one thing. When you marry the magnetism concept with the electricity concept, you get yourself a newly born baby called electromagnets. That's where all things started, and all hell break loose from there when they discovered that they can marry these two concepts. And because of this marriage, my friends, we created generators, we created motors, we created relays, contactors. So it's unreal, because electromagnetism is if this link, guys, here's my link. That link that connects the electricity into the mechanical movement, that link is right here, the link, whatever link it is, electromagnetism. What does that mean, Joe? I can convert electrical power through a motor into mechanical power, saw, pump, air conditioning, rooftop units. All these are mechanical equipment creating mechanical function, heat, cool, moving work, cutting 2x4s, but driven by electrical power. Why that? Because of the concept of the motor. What is the concept of the motor? The concept of the motor is based on the electromagnetism. Very, very powerful concept, guys. So then, when they discover, guys, electromagnets, these guys are not natural. They become magnetized as long as they have a current around it. So that's when they discover that if they can put an electrical current around an object, they can magnetize this object. So if I can put a coil here and move it and bring a power right here, 120, I can create an electrical magnet. And from the electromagnet, guys, I can create a mechanical motion. So you converted electrical power into mechanical power. The versa is true, guys. I can make an electrical motion, mechanical motion, diesel engine, turbine, driving an alternator to create power, the opposite. So I can go this way, get mechanical motion, or I can go the other way from mechanical motion and can create electrical power. Very interesting. Okay, they have amp turn, guys. Very interesting concept, determined by multiplying the number of turns by the wire by the current that flows over them. Electromagnets are proportionally, so the higher the amp turns, so if you have 5 turns in a coil, multiplied by the 2 amps that go through it, that'll give you 10 amp turn. The higher the amp turn, the bigger, the stronger the electromagnet. The stronger electromagnet. They start adding material, guys, inside the magnet to make the electromagnet stronger. What they did that, so instead of just having a coil, as you can see here, just one coil, the flux of line describes how powerful the magnet that you're creating is. If you put a material inside it, you can create a more powerful electromagnet. And then they come up with the concept, guys, of relays and magnetic starters or electromagnetic starters and so forth. with magnets. So they start creating, the idea, guys, is to create a magnetic electrode that's so powerful they can push two big fat NEMA 7, NEMA 8 contactors to shots and pull them apart to orbit. That's like electromagnetic force, right? Or I create a bigger electromagnet that can pump water from, you know, say 5-gallon pump, floor 0 all the way to floor 15. So it has to have a very powerful motor, which is creating a very powerful electromagnetic force that can pull this stuff. Okay, with the core material, guys, there's something called permeability and reluctance. Permeability is the willingness of the material to become magnetized. And reluctance is the opposite, the resistance to be magnetized. The resistance of the material to become magnetized. Who cares? This is how I can create relays, coils, and contactors, and generators. If the material can be easily magnetized, I can make a better generator, a better relay, a better contactor, a better coil. Not then I have to look for a material I can magnetize better. So permeability versus reluctance. Any question, guys? Permeability versus reluctance. Anything about permeability versus reluctance? Permeability is good, of course. And there's the concept of saturation. After a certain amount of time, guys, no matter what you do to the molecules, you cannot align them, line up enough to get more magnetism out of the material. So enough is enough. That material is drunk and saturated. No matter what you do to it, it's saturated. You cannot make it more or more magnetic or more magnets out of that. So saturation, you reach the enough point. Enough is enough. So the muzzle magnets they're not going to line up more, and you're not going to get a better magnet out of this material. You reach the saturation. Okay, and when you move the power, the electrical power, out of the material, there will become residual magnetism. They call residual magnetism. That's basically the leftover magnetism after you remove the force that magnetized the material. For example, after Jacob, you turn the switch off, the material inside of the coil will still have some magnets inside it, very small amount. This is called residual magnetism, leftover. After you turn the power off, no more electromagnets, stop. There's some magnetism left in this material. They call the residual magnets. Any question, guys, about saturation and residual magnets? Saturation and residual magnets. Saturation and residual magnets, my friends. So on the magnets, guys, measurement. We measure the magnets in the English concept with the concept flux. The bigger the flux, the better magnet you have created. A couple of other and so forth. Places where in French places where they can measure them in meter kilogram second, or centimeter gram second. But the most common, at least in the U.S., common unit that we use is the flux. Polarity. If you want to measure, I don't know if we have, to measure a magnet. So I have a coil like this. I have a coil and the current, and to know where's the north and the south of this coil. So if I can go grab a highlighter, I know that the current is going. It's really hard to decide that one. Okay, let's go more. Okay, so I'm going 1, 2, 3, 4, 5, and move on. Here's my coil, and I'm going to test where the north and the south of this coil goes. My current is coming from here, going up, and again, up and again, and you can see how the current is going. The way I measure it, up and back into that source. So you have your fingers pointing. So the current, if you guys, your left hand rule, they call it left hand rule. If the left hand rule is pointing towards the current moving in this coil, in my case, the current is coming out of the it's going this way, so it's moving toward me. Then in this case, the north pole would be, my thumb will be pointing to the north pole. And if you're in the north pole, what do you think the south pole would be? The south pole. So this is, okay, identifying the poles of electromagnets by using the left-hand rule. The left-hand rule. There's a nicer picture, guys, in page 107. Nicer picture in page 107, fig 417, and you see how if the current, your finger is pointing towards the flow of the current in the coil, then your thumb will be pointing towards the north pole of that electromagnet. Okay, that's how we can strengthen magnets and identifying which pole is this magnet, north or south. So we can interact it with other poles, so you can get us a spin of a motor or a spin of a generator or a movement of a magnetic contactor, relays, or coil. And about this rule, left-hand rule, anything about the left-hand rule. You have a material that's magnetized. Can I demagnetize the material? No problem. When the molecules of the magnetized objects are disarrayed or disarranged as they are in non-magnetized material, can demagnetizing it. Devices to do this to demagnetize, use the hammer and keep hitting it and heating, and you know, by first demagnetizing. Here's a couple of pictures, guys, in page 05. You can heat and physical building on these equipment to demagnetize it, change it from a magnet into a non-magnet. That's the caveman way of doing it. So caveman is to grab your hammer, stand hammering that thing until you get it, or you have some light underneath it, you heat it. Or 21st century way of magnetizing and demagnetizing objects, guys, is you can have stator. You can put the object inside that stator electrically. Here's my magnet right in here, and I bring a current. By bringing the current, guys, in, I can, and with current limiting and so forth, you can treat that magnet electrically to demagnetize it. You have a picture on page 108, guys. If you're looking at it, you set object, this object into this stator, single phase stator winding. You analyze the winding. You create a magnetic field that basically screw up rearrange and screw up the alignment of all these molecules in the serial and make it a string molecules, and off you go with a non-magnetic material. Any, my friends, any questions? Care, guys, about magnets. This is basically why we did what we did here. Number one, because of electromagnets, measuring instruments, inductors, transformers, motors, speakers, generators, all guys are a part of electromagnetic system. Let's emphasize, because electromagnetic system can convert. So look at this one, for example. Here's my system here. I can go this way and create a motor, or I can go this way and I create a generator, right? I can, by having a prime mover, like diesel engine, I can move an alternator to create power, or I have an alternator, I can move a motor to create a mechanical movement, which could be translated into air handling unit, impeller, into pump, into fan, into whatever mechanical force that you want it to go. Question guys about the application of the magnetic devices or electromagnetic devices. When you go with Mr. Filgic in year 4, you study motors, you're going to remember Chad telling you that this is the beginning of generators and transformers, is the electromagnets. You have a coil and you energize the coil across an object. Here's my piece of steel, and I grab my coil over here and I wound my coil around it, and my friend, and if you that one, you bring a current, say 10 amps over here. Now I can, with special design, I can make this piece of equipment move. Who cares if it's move or not? Now if you can capture that movement, and as it moves, there's two contacts here, guys. See that? And you take him here. Here's my 20 amp circuit. As this moves, it closes these contacts together. This is the concept of relay. You have just created a magnetic starter or a coil or relay. It's one concept of application of it. If I have two of these guys side by side, so that's the relay. If I put one here and one here, and I have one coil going this way, one coil going this way, and guess what? This is, you created a transformer. You just created a transformer through electromagnetic equipment. So I can't emphasize, guys, the most important thing, magnetism is the bridge that happens between electricity and magnetism to create electromagnetism. Electromagnetism can convert mechanical energy into electrical energy, or vice versa. That's enough about magnetism, guys. We spend probably 2 hours when we teach these classes about magnetism, but for us, they're good enough. Any question, guys? Any question about magnetism? Any question about magnetism? Or we let you go with the poll and have my fourth poll. My fourth, guys, is 5. Give you 5 minutes and go ahead and just answer these 5 questions about magnetism. Then we move, after that, we're going to move into the resistor. I know you guys wait before we get into the resistor. The resistor. Okay. Again. Okay, so that's a really good few questions, guys, reviewing the about magnetism. Don't look at question number 5, which is the force of 1 ounce. That was an interesting question, but for the most part, for the rest of them, guys, will be good review for the magnetism. Any question, guys, about magnetism? Anything about magnetism? How about it, Chad? Make sure you're still with me. Part of the night, guys, we're going to spend it with resistors. Maybe one of the single most important part, Matthew, of any electrical circuit is the resistors. Next week, we're going to be using resistors and put the series and parallel and analyzing circuits based on putting these resistors in circuits. So most basic electrical equipment, easy to analyze, easy to work with, coils and capacitors. Resistor works perfect with DC, perfect with AC. So that's why we're going to be starting it. Electrical circuit is starting point for the electricians, as we guys know. Well, at least on lab part. Resistance electrical. Okay, you have solid beginning of your education. So let's start, guys, without getting into all this. Will help us analyze series parallel circuits. If start you, Joe, with an impedance, and you get so confused because you tell me, Chad, oh, what the heck is an impedance? Resistance is very easy, very simple. It's linear. It goes in one direction. It works with AC and DC alike. It's a natural phenomena. You can measure it. You can ohm it. Unlike the inductance and the capacitance, which is electrical phenomena, which you cannot measure it with a device unless you are energizing that coil. So coil, the inductance of a coil and the capacitance of a capacitor, these are not natural phenomena, guys. It's electrical phenomena. That's why we start always with the resistor. Use a resistor if you're using it as a load. We can limit the current to a circuit. Through the circuit, guys, is a big concept because that's what a fuse and a circuit breaker does, right? A fast-acting circuit fuse, it's so fast that it will limit the amount of short circuit pumped into this equipment, and in return, you can expect that your equipment will survive and it's not going to be burned, and it will be protected by by a fuse circuit. I think the current, but really like a fuse, but that's what comes to my mind. The other one is voltage divider, guys. You can use a resistor to get multiple voltages from a system on the AC level. AC level, not a whole lot. Okay, let's go talk about different type of construction for resistors. So the coming slides, guys, and talk about different manufactured type of resistors. The first and the simple most one is called fixed resistors. So we make a fixed resistors. Fixed resistors, my friend, and you can use, look at the page, we have it over here. Here's what your fixed resistor. If you look at page 115, they have a cutout of this resistor. They have the lead. Okay, that's composition resistor, fixed resistors. So we have ohmic value, which cannot be changed. So that's why it's fixed, guys, because if it's a 5 ohm, good luck changing it unless you completely change the resistor. Carbon resistor components made out of carbon resistors. If you look at the 115, they have the lead, they have carbon wreathing compound, the insulators in it, and insulators around it. So they have the carbon as your resistive material, and they have your insulators around it, and leads to connect to it. If you 15, the cutout to it. So we have the lead to connect to it, the insulation to insulate, and inside the resistive material is carbon in this case. Carbon made in certain ways, I guess. Okay, what you're looking at, these are fixed value resistors. Very interesting, guys, for fixed value resistor. If it tells you half a watt, and these are not power with electronics, if it says half a watt, do not mess around and give it more than half a watt. Otherwise, what do? You burn it. What? Give it what? 2 watts? 2 watts. So these is the low voltage or resistors are marked with the amount of watt that they can consume. If you put them across a circuit that can pump more power into them, you just lost it with them. They also, guys, color coded. If you can look at the color in brands, there are 4 brands and 5 brands. And from the color, you can predict from table the value of these resistors. So from these colors, I can predict the ohm value of these resistors, and at the same time, they are watt limited. The watt limited, meaning you can't just pump any amount of power across them. You don't want to burn them. If you don't want to burn them, these are very interesting. The second part, so that's a fixed resistor. The second is metal film resistor, guys, constructed by applying a film or metal to a ceramic rod in a vacuum. There's a metal film resistor. If you guys look at the cover of that, so you can see the leads, you can see the outer cover, you can see the metal film, and so you have your metal film and ceramic rod. So there's ceramic rod, there's the metal film around it, and there's an outer covering for insulation, and you have the leads of the conductor. Tolerance indicate the plus and the minus limits of the resistor. Every resistor, guys, especially the low voltage guys, use them all the time. You're going to find the plus or minus 1%. This means if the resistor says 100 ohm, if you're in 100 ohm, we really have no idea. It could be 99 ohm or be 101. So I guarantee you it will work within that limit. 101 to 99 ohm if your resistor is 100 ohm with a tolerance of plus or minus 1, right? So you increase plus 100 is 1, so you add the 1, it becomes 101. You subtract the 1, it becomes 99. So that the tolerance range, it will work perfect within a 101 to 99. Any questions about the metal film resistor and the tolerance? The tolerance of these babies. Resistor. So twin film resistor, again fixed, made by coating the ceramic rods with a film of carbon instead of a metal. Now that's carbon film resistor, they have the carbon instead of a metal, as you can see the film. So they've had a lot of combination of them. So mixed glazed resistor, fixed, similar to the metal film, by combining metal with glass this time. So in page 14, guys, there's so many ways of basically to creating a fixed resistor. For the most part, if you can see, the common thing between them is an insulator and some type of highly resistive material. And carbon was one of them. Filmed carbon was one of them. Ceramic rod, that's another one of them. So you have to have a high resistive material with some insulator. These are the fixed ones. So the wire wound resistor. So it's a fixed resistor, and the wound is the insulator, guys, ceramic core made by winding of a resistive wire around a ceramic coil. You can see these are similar to the heaters, guys, the coil heaters that they use. So you can see an insulator right there, and right around it, a highly resistive material around it, and then you energize that baby. You put your 240 heat, and you got yourself a baseboard heater, basically. Very similar baseboard heater concept. Any questions? My friends, any questions? Okay, we read the color code for these resistors, guys. They have a 5 brand and a 4 brand. Look at the 5 brand reading for all these resistors. The fixed resistors. Here's your 5 brands. You have 1, you have 2, 3, 4, and 5. And these are, guys, the black is always number 0. Brown is 1, 2 is red, orange is 3, and yellow is 4. And that's value-wise. Tolerance is, here's where you get your tolerance from. And based on these guys, you can find, based on the color code and the location from left to right of the color, you can just we have an example in page. I don't know if I have that example. So okay, so we don't have the fixed value. So there's an example, guys, in page 123. If you guys go to page 123, please, and you see that there's a black, 2 brown, 2 blacks, and a brown and a brown in a brand. So if you guys go to analyze from the tables in page 121, you can find brown is always number 1 as the first band. Second band is black, always 0. 2 blacks is 0. And the third brand is so 1, 0, 0. And third brand is usually the multiplier, which is brown. That brown stands for 10, multiplier 10. So you multiply your answer by 10. So you get with 100, guys, because 1 brown, 2 black. Then multiply it by 10, so this resistor becomes 100 multiplied by 10, 1,000. The last brand is the tolerance. The tolerance is brown, and a brown can give you plus or minus 1%, as you can see. Brown as a tolerance can give you plus or minus. A black can give you a 0. A brown can give you a 1. So look at, I have 1 brown, 2 blacks, 0, 0. And the last brown is a multiplier, guys. When it's multiplier, if the brown is used as a multiplier, this means it's a 10. So that gets the 1,000 ohm with a tolerance, so plus or minus 1%. So this joule is going to be basically 999 or 1,001, somewhere in between. That's the acceptable tolerance as you install these resistors. Action, guys, about the tolerance. In an iPhone, there is an what do you call them? iPad for you, or what do you call these? We can get put all these coverage for all the resistors, and it tells you what the number is. What's the application? What do you call application? Everybody can chat with me here. I forgot the term that they use. Application, yes. What's the app. There's an app for you. Thank you. That's what we're looking for. There's been the iPhone. Teaching a class one time at Dunwoody, and one of the students pulled his iPhone, and he was able to identify from the app for identifying color coded resistors. There's an everything now. So, for the most part, guys, it's really not a whole lot unless you do low voltage. It's not a big deal for you. Also, resistors here reduce standard values, high tolerance, pure resistance value. For the fixed resistor, guys, really mostly with the low voltage fire alarm system, end of line resistor they use, telecommunication system, and so forth. For the power industry, they use a power resistors, which is different. Power rating. Power rating, guys, for resistor, as we said, every resistor has to have a power rating. You shall not be exceeded on the resistor. Here's how you find the power rating for a resistor. Either by I squaring the current, by squaring the current multiplying by R, squaring voltage multiplying it by dividing it by R, or the traditional way of E times I. All these will tell you that you cannot exceed the power rating of a resistor. So if my resistor is 10 watts, I can't pull 11 watts out of it and expect that baby to stay under. Move to the variable resistor, guys. Variable resistors, obviously, you can change. It can be changed and varied. Multi-term variable resistors, by moving a wiper arm with a rule of some number of turns, sensitive to adjustment. So then in page 127, guys, basically you have a resistor and you have an arm, and by moving that arm to different locations, you can get different value of resistor. What's good about one, guys? You can use a lot in an electronic industry for signals and tuning and all this good stuff. Big concept. Called potentiometer or pot or rheostat. These are very commonly used thermostats, guys, for variable resistor. A lot of radios and all these receivers and equipment, you have this resistor. By adjusting the resistor, you actually can tune yourself into WCCO, or you can tune yourself into 91.1 TV, public radio. You can tune yourself to a public radio. So that's where potentiometer and rheostat becomes very interesting in tuning signals to certain areas and so forth. Yes, any question, my friend? Any schematic for resistor? This is the schematic that we use for the resistor. If it's a coil, they use you can see that the coil looks something similar. So that's my schematics. Next week, my friend Ross, you're going to see Chad with resistor putting a couple of these, one in here and one in here, and bringing a voltage of 48 volt DC. Asking you to find the resistor. If you know the amps, and say 50 ampere, and say that resistor was 5 and that resistor was 10, I'm asking you to find the third resistor. Okay, so basically what resistor symbols is, guys, and you can add them together in series, in parallel. So easy to analyze circuits with resistors because, and so simple. So it's so simple because there's no impedance. It's linear and take a whole lot to analyze it. One more time, guys. Any question about resistors? Question about resistors? So to cope what we do, guys, we dug deep into the atomic theory, and we looked at the atom, the structure of the atom, the protons and the neutrons and the electrons, and we discovered that valence electrons, if it's fully loaded, means 7 or 8 is insulators. Half loaded 4 is a semiconductor. If it's lightly loaded, as in 1 or 2 or 3, they'll make it a conductor. material. They moved out, we grouped guys the electrons and we put them together in a pack and we called it column, and we moved that column that will create the amps, and they went into the Ohm law and power law and major quantities of the electrical equipment. Major quantities: the power, the voltage, the current, and resistance. We looked at different type of resistors, and then we moved into electromagnets, if you guys remember, and we talked about natural magnets, electromagnets, and we say because of electromagnets we enjoy the luxury of turning your air conditioning on and your heater in your car and all this good stuff. That's as a concept as a result of electromagnetism, really, in power industry. So basically that, and then we talked about the resistors, different type of resistor, and how the resistor is the simplest block of an electrical circuit, the simplest. Later on, guys, you can add the impedance with a reactance and a capacitance, and it becomes more sophisticated real application of a circuit. So as I said before, the last poll for the night, any questions about cover? Any questions? So 5 more, 10. I'm going to give you guys, these are 10. I'm going to give you 5 minutes to go start because lack of the time. So go ahead, guys, and start. Questions about the resistors, and then we'll wrap up for the night. Okay. Okay, almost there, guys. Okay. Okay, I hope you guys were able to see whatever sizes number 5 and number 6, how you can find the tolerance, the watt tolerance on these resistors. So question number 5, for example, you take the amps and you multiply it by the square, multiply it by a resistor, you find watt, and you should not exceed the watt rating of these resistors. In question number 8, you take 5% of the 10,000, that gets you 9,500, and below, and 5% above, that will give you 5,000. 1,500, and will be the tolerance for that resistor. The tolerance for that resistor. Let me grab these, shoot them your way. Any questions before I move on here? Any questions? How about an next question, Chad? Page 11.7, guys. There's really nice exercises that if we're meeting in person, we will do some of them. We were not able to do them even when we met in person at one time because of no lab. But do a favor, guys, read these page 11.17. Just to get an idea one time in your life, there's a few concepts about basic electricity and really concepts that should be introduced. Let me see what we have. Number 6. Explain number 6. Okay, let me go number 6. Go back. Number 6 of that poll, I believe. Number 6, it says, back. Okay. Number 8, number 7, number 6. Number 6, guys, it says a 1 watt 350 resistor is connected to 24 volts. Is this resistor operated within its limits? So the 24 volts and divided by number 6, what was the ohm, divided by the resistor, which is 350. Simply you want to find the power. And for this guy, for this one, you need to go to the power formula that says power equal the voltage, or E squared. You guys remember that one? E squared over R. That's the formula that you need to do. And if you do that one, basically should be your calculation. If you do square the power, so if I get my power 24 with my inverse squared by this one, or 24 with my square on this calculator times 24 divided by 350. Was it 350? Yeah, 350 equals. What's my answer for this one? So 350 rated for 1 watt, and it's operating at 1.6. So that's why it's exceeding its limit. Oh, basically that formula that you use. Any question, guys, before I let you guys go? Any questions? Okay, so next week we are going to go over, guys, series circuit. So we're building on these power and ohms formulas to analyze series and parallel circuits. Quick reminder, guys, March 15, for those of you who came, we'll be making up a class March 15 so we can finish on time by the end of April. So please plan accordingly. March 15, we will have a class. So the class will be March 8, and the one after March 15, and we'll continue in every Tuesday in March. Okay, that's, my friends, all I have. If you have any questions, call me. Otherwise, good night, and we'll see you next week.